Omniverse. Please enjoy.
阮兜做袂歹看吼。I want to speak to you in Chinese, but I have so much to tell you, I have to think too hard to speak Chinese. So I have to speak to you in English. At the foundation of everything that you saw was two fundamental technologies: accelerated computing and artificial intelligence running inside the Omniverse. Those two technologies, those two fundamental forces of computing are going to reshape the computer industry. The computer industry is now some 60 years old. In a lot of ways, everything that we do today was invented the year after my birth, in 1964. The IBM System 360 introduced central processing units, general purpose computing, the separation of hardware and software through an operating system, multitasking, I/O subsystems, DMA, all kinds of technologies that we use today, architectural compatibility, backwards compatibility, family compatibility, all of the things that we know today about computing largely described in 1964. Of course, the PC revolution democratized computing and put it in the hands and the houses of everybody. And then in 2007, the iPhone introduced mobile computing and put the computer in our pocket. Ever since, everything is connected and running all the time through the mobile cloud. This last 60 years, we saw several, just several, not that many actually, 2 or 3 major technology shifts. 2 or 3 tectonic shifts in computing, where everything changed. And we're about to see that happen again. There are 2 fundamental things that are happening. The first is that the processor, the engine by which the computer industry runs on, the central processing unit, the performance scaling has slowed tremendously. And yet, the amount of computation we have to do is still doubling very quickly, exponentially. If processing requirement, if the data that we need to process continues to scale exponentially, but performance does not, we will experience computation inflation. And in fact, we're seeing that right now as we speak. The amount of data center power that's used all over the world is growing quite substantially. The cost of computing is growing. We are seeing computation inflation. This, of course, cannot continue. The data is going to continue to increase exponentially, and CPU performance scaling will never return. There is a better way. For almost 2 decades now, we've been working on accelerated computing. CUDA augments a CPU, offloads and accelerates the work that a specialized processor can do much, much better. In fact, the performance is so extraordinary that it is very clear now, as CPU scaling has slowed and eventually substantially stopped, we should accelerate everything. I predict that every application that is processing intensive will be accelerated, and surely every data center will be accelerated in the near future. Now, accelerated computing is very sensible. It's very common sense. If you take a look at an application, and here the 100T means 100 units of time. It could be 100 seconds, it could be 100 hours, and in many cases, as you know, we're now working on artificial intelligence applications that run for 100 days. The 1T is code that requires sequential processing, where single-threaded CPUs are really quite essential. Operating systems, control logic, really essential to have one instruction executed after another instruction. However, there are many algorithms, computer graphics is one, that you can operate completely in parallel. Computer graphics, image processing, physics simulations, combinatorial optimizations, graph processing, database processing, and of course, the very famous linear algebra of deep learning. There are many types of algorithms that are very conducive to acceleration through parallel processing. So we invented an architecture to do that. By adding the GPU to the CPU, the specialized processor can take something that takes a great deal of time and accelerate it down to something that is incredibly fast. And because the two processors can work side by side, they're both autonomous and they're both separate, independent that is, we could accelerate what used to take 100 units of time down to 1 unit of time. Well, the speed up is incredible. It almost sounds unbelievable. It almost sounds unbelievable. But today I'll demonstrate many examples for you. The benefit is quite extraordinary. 100 times speed up, but you only increase the power by about a factor of 3. And you increase the cost by only about 50%. We do this all the time in the PC industry. We add a GPU, a $500 GPU, GeForce GPU, to a $1,000 PC, and the performance increases tremendously. We do this in a data center. $1 billion data center, we add $500 million worth of GPUs, and all of a sudden, it becomes an AI factory. This is happening all over the world today. Well, the savings are quite extraordinary. You're getting 60 times performance per dollar. 100 times speed up, you only increase your power by 3x. 100 times speed up, you only increase your cost by 1.5x. The savings are incredible. The savings are measured in dollars. It is very clear that many, many companies spend hundreds of millions of dollars processing data in the cloud. If it was accelerated, it is not unexpected that you could save hundreds of millions of dollars. Now, why is that? Well, the reason for that is very clear. We've been experiencing inflation for so long in general purpose computing. Now that we finally determined to accelerate, there's an enormous amount of captured loss that we can now regain. A great deal of captured, retained waste that we can now relieve out of the system, and that will translate into savings. Savings in money, savings in energy. And that's the reason why you've heard me say The more you buy, the more you save. And now I've shown you the mathematics. It is not accurate, but it is correct. Okay, that's called CEO math. CEO math is not accurate, but it is correct. The more you buy, the more you save. Well, accelerated computing does deliver extraordinary results, but it is not easy. Why is it that it saves so much money, but people haven't done it for so long? The reason for that is because it's incredibly hard. There is no such thing as a software that you can just run through a C compiler and all of a sudden that application runs 100 times faster. That is not even logical. If it was possible to do that, they would have just changed the CPU to do that. You, in fact, have to rewrite the software. That's the hard part. The software has to be completely rewritten so that you could refactor, re-express the algorithms that was written on a CPU so that it could be accelerated, offloaded, accelerated, and run in parallel. That computer science exercise is insanely hard. Well, we've made it easy for the world over the last 20 years. Of course, the very famous cuDNN, the deep learning library that processes neural networks. We have a library for AI physics that you could use for fluid dynamics and many other applications where the neural network has to obey the laws of physics. We have a great new library called Ariel that is a CUDA accelerated 5G radio so that we can software define and accelerate the telecommunications networks the way that we've software defined the world's networking internet. And so the ability for us to accelerate that allows us to turn all of telecom into essentially the same type of platform, a computing platform, just like we have in the cloud. cuLitho is a computational lithography platform that allows us to process the most computationally intensive parts of chip manufacturing, making the mask. TSMC is in the process of going to production with cuLitho, saving enormous amounts of energy and enormous amounts of money, but the goal for TSMC is to accelerate their stack so that they're prepared for even further advances in algorithm and more computation for deeper and deeper, narrow and narrow transistors. Parabricks is our gene sequencing library. It is the highest throughput library in the world for gene sequencing. cuOpt is an incredible library for combinatorial optimization, route planning optimization, the traveling salesman problem, incredibly complicated. Scientists have largely concluded that you needed a quantum computer to do that. We created an algorithm that runs on accelerated computing that runs lightning fast. 23 world records. We hold every single major world record today. cuQuantum is an emulation system for a quantum computer. If you want to design a quantum computer, you need a simulator to do so. If you want to design quantum algorithms, you need a quantum emulator to do so. How would you do that? How would you design these quantum computers, create these quantum algorithms, if the quantum computer doesn't exist? Well, you use the fastest computer in the world that exists today. And we call it, of course, Nvidia Cuda. And on that, we have an emulator that simulates quantum computers. It is used by several 100,000 researchers around the world. It is integrated into all the leading frameworks for quantum computing, and is used in scientific supercomputing centers all over the world. cuDF is an unbelievable library for data processing. Data processing consumes the vast majority of cloud spend today. All of it should be accelerated. cuDF accelerates the major libraries used in the world. Spark, many of you probably use Spark in your companies. Pandas, a new one called Polar, and of course, NetworkX, which is a graph processing database library. And so these are just some examples. There are so many more. Each one of them had to be created so that we could enable the ecosystem to take advantage of accelerated computing. If we hadn't created cuDNN, CUDA alone wouldn't have been possible for all of the deep learning scientists around the world to use, because CUDA and the algorithms that are used in TensorFlow and PyTorch, the deep learning algorithms, the separation is too far apart. It's almost like trying to do computer graphics without OpenGL. It's almost like doing data processing without SQL. These domain-specific libraries are really the treasure of our company. We have 350 of them. These libraries is what it takes and what has made it possible for us to have such open so many markets. I'll show you some other examples today. Well, just last week, Google announced that they've put cuDF in the cloud and accelerate Pandas. Pandas is the most popular data science library in the world. Many of you in here probably already use Pandas. It's used by 10 million data scientists in the world. Downloaded 170 million times each month. It is the Excel, it is the spreadsheet of data scientists. Well, with just one click, you can now use Pandas in Colab, which is Google's cloud data centers platform, accelerated by cuDF. The speed up is really incredible. Let's take a look. That was a great demo, right? Didn't take long. When you accelerate data processing that fast, demos don't take long. Okay, well, CUDA has now achieved what people call a tipping point, but it's even better than that. CUDA has now achieved a virtuous cycle. This rarely happens. If you look at history and all the computing architectures, computing platforms, in the case of microprocessors, CPUs, it has been here for 60 years. It has not been changed for 60 years. At this level, this way of doing computing, accelerated computing, has been around, creating a new platform is extremely hard because it's a chicken and egg problem. If there are no developers that use your platform, then of course there will be no users. But if there are no users, there are no install base. If there are no install base, developers aren't interested in it. Developers want to write software for a large install base. But a large install base requires a lot of applications so that users would create that install base. This chicken or the egg problem has rarely been broken. And it's taken us now 20 years, one domain library after another, one acceleration library another, and now we have 5 million developers around the world. We serve every single industry, from healthcare, financial services, of course the computer industry, automotive industry, just about every major industry in the world, just about every field of science. Because there are so many customers for our architecture, OEMs and cloud service providers are interested in building our systems. System makers, amazing system makers like the ones here in Taiwan are interested in building our systems, which then takes and offers more systems to the market, which of course creates greater opportunity for us, which allows us to increase our scale, R&D scale, which speeds up the application even more. Well, every single time we speed up the application, the cost of computing goes down. This is that slide I was showing you earlier. 100x speed up translates to 97, 96%, 98% savings. And so when we go from 100x speed up to 200x speed up to 1000x speed up, the savings, the marginal cost of computing continues to fall. Well, of course, we believe that by reducing the cost of computing incredibly, the market, developers, scientists, inventors will continue to discover new algorithms that consume more and more and more computing, so that one day something happens, that a phase shift happens, that the marginal cost of computing is so low that a new way of using computers emerge. In fact, that's what we're seeing now. Over the years, we have driven down the marginal cost of computing in the last 10 years in one particular algorithm by 1 million times. Well, as a result, it is now very logical and very common sense to train large language models with all of the data on the internet. Nobody thinks twice. This idea that you could create a computer that could process so much data to write its own software, the emergence of artificial intelligence was made possible because of this complete belief that if we made computing cheaper and cheaper and cheaper, somebody's going to find a great use. Well, today, CUDA has achieved the virtuous cycle. Install base is growing. Computing cost is coming down, which causes more developers to come up with more ideas, which drives more demand. And now we're in the beginning of something very, very important. But before I show you that, I want to show you what is not possible if not for the fact that we created CUDA, that we created the modern version of the modern big bang of AI, generative AI. What I'm about to show you would not be possible. This is Earth 2. The idea that we would create a digital twin of the Earth, that we would go and simulate the Earth so that we could predict the future of our planet to better avert disasters or better understand the impact of climate change so that we can adapt better, so that we could change our habits now. This digital twin of Earth is probably one of the most ambitious projects that the world's ever undertaken, and we're taking large steps every single year, and I'll show you results every single year, but this year we made some great breakthroughs. Let's take a look.
On Monday, the storm will veer north again and approach Taiwan. There are big uncertainties regarding its path. Different paths will have different levels of impact on Taiwan.
想象一个我们能够预测未来的世界，数位孪生反映真实情况的虚拟世界，让我们看见未来。数位孪生是一种反映真实世界的虚拟模型，让我们能够从今天的行为来预测对未来世界的影响。介绍一下 Nvidia Earth 2， 一个利用 AI、物理模拟和电脑图形技术来预测全球气候的数位孪生。CoreDiff 是 Nvidia 的生成式 AI 模型，它在 WRF 数值模拟的基础上训练而成，能够以12倍更高的解析度生成天气模式，从25公里提高到2公里，这代表了区域天气预测的一个巨大飞跃。令人惊讶的是 ，CoreDiff AI 比传统的物理模拟方法快1000倍，且能源效率高3000倍。在台湾的中央气象局是用这些模型来更精确地预测台风登陆点。但我们并不止步于此，下一个前沿是超本地预测，能精确到数十米，并考虑到城市基础设施的影响。CoreDiff AI 还在使用像是 Palm 生成的高解析度数据进行训练，一个极高解析度的物理模型，用于模拟大气和海洋边界层。当与天气模拟风场结合一起时，它可以模拟建筑物周围的气流。单极强风汇聚的情况，我们预计能够预测像下冲这样的现象。当强风汇聚到街道层，会有可能造成腐坏并影响行人。Nvidia Earth 2是一个绝佳范例，它融合了人工智慧、物理模拟和观测数据。可以帮助国家和公司预见未来，并应对极端天气的影响。
I wrote it, but Jensen AI had to say